I will talk about simulation, and especially simulation for the autonomous driving revolutions. And what I mean behind this is how the simulation can help and support the development of all this advanced technology in order to achieve the promise to put on the market such kind of new technology with a level of safety as requested by the market. So my talk will be in connection with cooperative, connected, and I would say automated mobility. First will be autonomous vehicles, because the only way to achieve the safety of a vehicle, of autonomous vehicle, is to use simulations. And then I will give you a flavor of what we can do as well at ANSYS in order to support different activities in the deployment of the cooperative ITS, and especially how to use physics-based simulations at the system level. And at the system level, we can achieve a complete testing or evaluation of potential impact of the future deployment of these new technologies. So let's talk about autonomous vehicle first. And just a simple fact. The fact is, when we are talking about the different level of autonomy, so the SIE has been defined at 5 levels of autonomy, from level 1 up to 5. So when we are talking about an autonomous shuttle, as yesterday, it's an autonomous, no steering, no pedals, it's a level 5. Your car you are driving today is probably a level 1 or 2. Maybe you have the chance to drive a very advanced car with an autopilot or something like this, which looks like level 3, but in fact it's a level 2 in Europe. As soon as you achieve the level 3, you need to achieve a certain level of safety, because you give the responsibility of driving to a car, to the vehicle, not to the driver. So from level 3, level 4, and level 5, you have less and less responsibility of the driver and more responsibility of the car. And in that case, testing to achieve the level of safety to release such kind of autonomous vehicle requests a certain amount of real testing and real driving. And Mr. Toyoda-san, from the CEO of Toyota, just gave this as an estimation, saying that it's probably, we are talking probably about 8 billions of miles testing on the road to ensure the ASIL-D level of safety. So one of the companies which is probably the most advanced today on the market is Waymo, and Waymo achieved 10 million miles in 10 years. So to achieve this and to realize the promise of autonomous driving cars and a level 3 on the market in 5 years from now, the only way to achieve this testing and validation is doing on virtual environment, on simulation. And this is exactly what we are doing at ANSYS. We are a worldwide simulation company with a complete portfolio on the different physics which are requiring. So from the structures, fluid, electromagnetism, semiconductor, and optical simulations into a complete component simulation detail up to a system level simulation. And this is an important aspect, and we are assembling this simulation component into a complete comprehensive platform where we address this testing requirement, including, including the sensors, a level 3. So today, a level 2 cars, you have probably, if I remove the ultrasonic sensors for your parking assist, so you have radar and camera. maybe 1 to 6 sensors maximum on your car today. For the level 3, you will get probably 20 to 25 sensors on your car, which means that you have 20, 25 eyes on your car to feed the decision making of the vehicle. So sensors is a key aspect, and simulating all the detail of the sensors to understand all the worst case and corner cases is a key aspect. So we assemble simulation of the sensor into a complete virtual environment platform for testing in connection with functional safety and the embedded software generation tool, connecting with the cybersecurity evaluation and electronics design and reliability. So this platform is available, as we can see on this video. So here, it's a complete virtual driving where we bring our an ACC software inside the scenarios. So the scenarios has been built reproducing a virtual environment. So here in the case, it's a city. The sensors are setting up on the car, on the Ego car. And we simulate all the driver behavior, all the scenarios and situation, and all the sensors. And then we can prepare scenarios. So scenarios is like here in that case. So you have your car following another one with an adaptive cruise control function. So in that case, it's a basic level 2 car, function. And then you have an emergency braking function activated by the detection of a pedestrian. So something really simple. The complexity behind such kind of scenarios is the variability you need to achieve for testing and to achieve the robustness of the function. And the variability depends on the environment, so of the weather conditions, of the different function inside the car. So just variability. So in this basic example, you have same scenarios, which is the original scenarios, and we just put one variable, which is having a wet road instead of a dry road. So with a low grip road, we reproduce the same scenarios, and then we can see how it reacts. So in that case, no change in the embedded software, and you achieve an accident. And in the last case is with the implementation of a specific embedded software, what we call the safety gate software, in order to anticipate such kind of event. So basically here you have seen one scenarios derivated into two scenarios. And our simulation platform is able to take hundreds and thousands of variables. So when we are talking about weathers, we are talking about speed of vehicles, number of pedestrians, number of cars, and then we can generate millions and millions of scenarios where we can test and evaluate the safety of the embedded software. And this is the way we are building our platform, and this is the way we are implementing this platform with major OEMs and suppliers in order to be in place when the level 3 cars will hit the road. And now, if I'm digging more on the sensor, it's an important aspect, as because I was talking about 20, 25 sensors on a car for level 3. We are talking about more than 30 for level 4. We are talking about radar, camera, LiDAR, ultrasonic as well. And all these sensors give some redundant informations and have different behaviors in different conditions. So a camera is good for classifications and identification of objects, but the camera is very poor as soon as you have fog or rainy conditions compared to a radar, but the radar is not able to well discriminate the object. So you see there is something, but you don't know what kind of thing it is, so you cannot read the signs and the road. And the LiDAR is also a mix of them. So it's now all considered by most of the industry that all these three sensors will be absolutely required as soon as you need to achieve the level 3 and level 4. Which means that for each scenario, you need to consider how the sensor will react and how the sensor will behave according to the artificial intelligence which is behind each sensor. So in terms of testing, it's really, really complex because for an integrator, for an OEM, an automaker, he has to know or he has to validate an implementation of a sensor setup with a function, with a level 3, level 4 functions, considering all worst case and edge cases depending on such kind of technology. So the only way to achieve correct simulation is to well implement the physics and the behavior of each sensors. That's the reason why we bring the physics into our simulation platform for all these three sensors. And then we can work and propose to the complete supply chain from tier 2 to OEMs, a complete process, an automated process where we can support the engineers in the component development, engineers in the vehicle integrations, and engineers in testing driving scenarios. So different levels, different actors in the industry, but at the end, making sure that the release car on the market is safe enough. So in terms of workflow and process, we are supporting very detailed, with very accurate simulation, all engineers working on the radar design, from the antenna up to the integration of the car, and finally up to the generation of the scenarios. And each of them requires a certain level of detail of the simulation. So here we are talking about people developing an antenna, making sure that the antenna is good enough according to the requirement. Here, it depends on the integration on the car first here. For example, the radar, when you put a radar at a certain position on the car, the performance of the radar will change depending on the car integration. And this change impacts the performance into the scenario. So for a simple case, depending where the OEM put the antenna on the car, the detection of an obstacle could be different in terms of distance of perception or identification could be different. So that means that even if you have developed your functions, level 3, based on a certain radar, if you implement this radar into a sports car or into a SUV, probably the function will not react as well and same. So that's important to consider. So that's the reason why this process is well done to support each stage of the development of a vehicle. And then we go up to a complete scenario simulation. So I will skip this one and bring you to this one. So here we bring the radar in conjunction to the camera into a driving scenarios. So preparing the scenarios, putting the sensors according to the position on the car, and generate and produce the scenario and the result. And all done in an automatic way as much as possible in order to achieve these million miles of testing. So for the camera, we are supporting exactly the same process from very detailed simulation on the optical imager simulation based, vehicle integrations. So today it's quite easy. You have one camera behind your windshield. But tomorrow you will have between 6 to 9 or 10 cameras on the car, and the implementation will depend on how you implement how the OEM implement the camera inside, and the performance will depend on this integration. So same, we will bring this camera into the scenario afterward. And when we are talking about camera simulation, we are talking about the edge cases and the worst cases. Then what our customers are requesting is really to simulate the physics and the worst case and edge case. So here is what we can achieve into a game engine and using very good and nice graphics. And here is how we simulate the physics on the camera in order to stimulate the artificial intelligence detecting or not the environment object. So that's a key aspect. And when we are talking about integration on a car, most of the OEMs, they will not want to show all sensors out of the car. They don't want to have a big LiDAR on top of the roof. And all sensors will be well packaged and integrated into the car. That's one of the key aspects. And to do this will require also some specific integration tools, simulations tools to validate the integration and the packaging. And here we can see some example. So a lot of OEM are thinking now how to integrate all sensors into the corner of the car, into the headlamp, the tail lamps, in order to have a sort of intelligent corner or smart corners. So here is an example of how to design a headlamp with the lights, the LiDAR, and a camera. And then, as soon as it's integrated, you can simulate how, for example, this camera can see the output on different day and nighttime conditions, but also in different weather conditions, and how it impacts the performance again. Same for the LiDAR. I don't go in much more detail of this, but here is exactly the same scenario as you have seen before, but in that case, you have still one camera and three LiDAR on the car. So it's exactly the same scenario, but with a different sensor setup and sensor layout, which make possible to validate the functions according to a different sensor layout. So this was to give you an overview of what we are doing and achieving with simulation for autonomous driving testing. So this platform is today under deployment into the industry at different level of testing, a different level of the supply chain from the tier 2 up to OEMs. And we are also working with different actors, especially in the domain of the V2X, where simulation can be also seen to evaluate and to anticipate the impact of the cooperative ITS deployment. And when we are talking about this, when we are a simulation company, usually we are asking for how the deployment of ITS will impact, I would say, will impact the infrastructure, will impact the people. So in that case, there are a lot of questions on the table. Question about the technology. So just a V2X communication can be based on a DSRC or a 5G LTE. But if you want to deploy thousands of antennas on the road, you need to make sure that in the different worst case or edge case, such kind of technology can give the correct answer. It's also for the link to the deployment and the adoption inside the vehicle or the deployment of the antenna will be also part of the discussion. Maybe 100% of the car will be equipped in 20 years from now, but what will happen in 5 years or in 10 years when you will have 20% or 50% of the car equipped with the V2X functions. And also what happened in all defects of the technologies. So all these questions can be addressed or evaluated or anticipated using simulation. And same, using simulation at two levels, at system level, when we see the global system, and we can see how the system will interact and what will happen in a case of a system defect or a subsystem defect. And then we are going in more detail at the component level in order to support the technology design and the component design, for example, an antenna or sensors, as I showed you previously. So here I have a video. If the video starts, yeah. So here is a video. So this is exactly the same simulation platform as you have seen. And here we have an example where driving into an highway, arriving onto an accident situation, and then the accident happened. And connecting with the V2X communication here, we are connecting with a network simulators, simulating the V2X communication, and when using this according to the infrastructure deployment of the antenna, we can show how the information will be captured back to the supervision system and then spread back to the vehicles. So this basic example shows how we can connect vehicle simulations with infrastructure simulation and network simulation. And here it's an example, another example, which has been done by a French consortium in order to use this. So vehicle simulation equipped with specific ADAS functions. It's a connected ACC. So the connected ACC make possible to automatically adjust the vehicle speed according to the traffic conditions. So connecting to this environment simulators and the vehicle ADAS simulators, we can see at global level, at system level, how this will impact the traffic flow. So in that case, for example, here, so the consortium was called Cinetic in France, and it was shown that, so this is a standard situation where you have your ACC with no standard ACC. So some vehicles are equipped with the ACC and some are not. And at the global level, at the city level, I would say traffic level, we can see a certain volume of traffic jam. And when we equipped part or a certain percentage of vehicle with this connected ACC, we can see for sure the elapsed time between vehicles reducing. And globally, we can see that the volume of traffic jam reducing as well, because the traffic flow is smoother in such kind of particular situation. So this project was led by Renault in connection with IFSTAR in France, and this group has been working also to demonstrate to the Paris region how such kind of technology could help also to smoother the traffic flow. So that's an example how to use simulation at system level. And for sure, when we are going more detail for engineering and design, we can go in very, very detail of V2V communication. For example, here based on a DSRC. So you have two cars equipped with a DSRC antenna, and these two cars can be in these two cars, in this scenario can be used to evaluate the impact of a specific DSRC antenna design deployed into specific junction. So here in that case, we are more in the component design and supporting the engineer designing such kind of antenna. Okay, that was to give you a global overview of our simulation approach at different levels, system level and detail level, in order to support the deployment of these new technologies. Thank you.